Have you ever wondered what lies above and below our solar system? Not just north or south on a map, but truly above and below in the cosmic sense? The answer will shatter everything you thought you knew about our place in the universe. Because out there, beyond the familiar plane where planets dance around our sun, exists a realm so vast, so mysterious, and so full of wonders that it makes our entire solar system look like a single grain of sand on an infinite beach. If you're fascinated by the hidden dimensions of our universe and want to explore more cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. Now let's begin. First, we need to understand something fundamental. Our solar system isn't just a random collection of planets scattered around the sun. It's a flat disk, almost like a cosmic vinyl record spinning in space. All the planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, orbit roughly in the same plane. This plane is called the Ecliptic, and it formed this way because our solar system was born from a spinning disk of gas and dust 4.6 billion years ago. But here's where it gets interesting. While we often picture space maps as flat, the universe is gloriously three-dimensional. And once you venture above or below this planetary plane, you enter a realm that most people never even think about. Let me take you there. Directly above and below our sun's poles, something extraordinary happens. The Parker Solar Probe, launched in 2018, has given us our first close-up views of these regions. Above the sun's north pole and below its south pole, massive jets of charged particles stream outward at speeds of up to 800 kilometers per second. These polar coronal holes are like cosmic fire hoses, spraying solar wind into space in directions perpendicular to where all the planets orbit. The European Space Agency's Solar Orbiter mission is right now capturing images of these polar regions that we've never seen before. What they're finding is revolutionizing our understanding. The sun's magnetic field lines emerge from these poles like the lines of force you see when you sprinkle iron filings around a magnet, but on a scale so vast that Earth would be a tiny speck in comparison. As we journey further from the sun, staying perpendicular to the planetary plane, we encounter something even more fascinating: the Heliopause. This is the boundary where our sun's influence meets the interstellar medium, the space between stars. The Voyager 1 and 2 spacecraft, though they traveled mostly along the ecliptic plane, have given us clues about what exists in all directions around our solar system. Above and below the solar system, the Heliopause takes on a different character. Recent data from the Interstellar Boundary Explorer, or IBEX, shows that the shape of our solar system's protective bubble isn't spherical as we once thought. Instead, it's more like a deflated croissant, compressed by the interstellar magnetic field. The regions above and below the ecliptic plane experience different pressures and particle densities than the regions along the plane. But let's venture even further. As we travel perpendicular to our solar system's plane, we begin to encounter the true citizens of the space above and below, the Oort cloud comets. This vast spherical shell of icy bodies extends perhaps 2 light-years from our sun in every direction, not just along the plane where planets orbit, but in a complete sphere. The Oort cloud is like a cosmic snow globe surrounding our entire solar system. While the planets are confined to their flat disk, these trillions of comets exist above, below, and all around us. When we see a long-period comet like Hale-Bopp or Neowise, it's often falling toward the sun from high above or below the planetary plane, diving through our flat solar system like a cosmic diver plunging through a floating disk. What's truly mind-blowing is that some of these comets have orbits tilted at 90 degrees to the planets. Comet C 2019 Y4, discovered by the Atlas survey, plunged almost straight down through the solar system plane before swinging around the sun. These perpendicular travelers are messengers from the spherical realm, that exists above and below our flat planetary neighborhood. As we continue our journey upward or downward, since direction loses meaning in space, we encounter our first stellar neighbors. But here's something that will blow your mind. The nearest stars to our solar system aren't arranged in a flat plane like our planets. They're scattered in 3 dimensions all around us. Proxima Centauri, our nearest stellar neighbor, at 4.24 light-years away, sits at an angle of about 62 degrees below the ecliptic plane. If you could draw a line from our Sun to Proxima, it would point distinctly downward from the plane where Earth orbits. Meanwhile, Barnard's star, our 4th nearest neighbor, lies about 14 degrees above the ecliptic. This 3-dimensional arrangement becomes even more dramatic as we zoom out further. The Gaia Space Telescope, launched by the European Space Agency, has created the most detailed 3-dimensional map of our stellar neighborhood ever made. It shows that stars above and below our solar system follow their own paths through space, some diving through the galactic plane, while others soar high above it. Wolf 359, a red dwarf star just 7.9 light-years away, sits almost directly above our solar system's north pole. If you could travel straight up from the Sun, perpendicular to all the planets' orbits, Wolf 359 would be one of your first stellar stops. It's like having a cosmic neighbor living in the apartment directly above you, while all your other neighbors live on the same floor. But the real spectacle begins when we zoom out even further and see our solar system's position within the Milky Way galaxy. Our entire solar system, along with all those nearby stars, is embedded in the Orion arm of our galaxy, about 26,000 light-years from the galactic center. And here's where our journey above and below takes on epic proportions. The Milky Way galaxy, our cosmic home, is also a flat disk, but one so vast it makes our solar system's disk look like a microscopic speck. This galactic disk is about 100,000 light-years across, but only about 1,000 light-years thick. Imagine a dinner plate scaled up to cosmic proportions, and you'll have a good mental model. Our solar system sits within this disk, but tilted at an angle of about 60 degrees to the galactic plane. This tilt means that as our solar system orbits the galactic center, a journey that takes about 230 million years, we actually bob up and down through the galactic disk like a cosmic carousel horse. Right now, we're about 50 light-years above the galactic midplane and rising. In about 30 million years, we'll reach our highest point, about 250 light-years above the galactic plane, before beginning our descent back down. Speaking of our solar system's incredible scale and our place within it, if you're fascinated by these cosmic perspectives, check out my video, How Big is the Solar System, and Why We Will Never Leave It. It explores the mind-boggling distances within our own cosmic backyard and why they present such incredible challenges for human exploration. The link is in the description below and pinned on the comments. Now, what exists above and below the galactic disk is where things get truly spectacular. As we rise above the Milky Way's plane, we enter the galactic halo, a roughly spherical region that extends hundreds of thousands of light-years in all directions. This isn't empty space. It's populated by some of the universe's most ancient and mysterious objects. Globular clusters are among the most stunning residents of the galactic halo. These are dense spheres containing hundreds of thousands or even millions of ancient stars, all bound together by gravity. Messier 13, the great globular cluster in Hercules, hovers about 25,000 light-years above the galactic plane. When you look at it through a telescope, you're looking up, out of our galaxy's disk, at a stellar city that's nearly as old as the universe itself. The Hubble Space Telescope has captured breathtaking images of these globular clusters, revealing that they're not randomly distributed. Many follow elongated orbits that take them high above and far below the galactic plane. Omega Centauri, the largest globular cluster visible from Earth, contains about 10 million stars and swings through an orbit that carries it 17,000 light-years above and below the galactic disk. But globular clusters aren't the only inhabitants of this vertical realm. The galactic halo is also home to mysterious streams of stars, the remnants of smaller galaxies that our Milky Way has torn apart and consumed over billions of years. The Sagittarius stream, discovered in 1994, wraps around our galaxy in a path that takes it far above and below the galactic plane. It's like a cosmic river flowing through three-dimensional space, a ghost of a galaxy that once was. The Sloan Digital Sky Survey has revealed dozens of these stellar streams, each one telling a story of galactic cannibalism. Some, like the Orphan Stream, loop high above the galactic North Pole before diving back down below the South. These streams are like cosmic archaeology, showing us the Milky Way's violent past, written in the paths of stars. As we venture even further above and below our galaxy, we encounter one of the most mysterious components of the universe: dark matter. While we can't see dark matter directly, we know it exists because of its gravitational effects. The Milky Way is embedded in a massive dark matter halo that extends far beyond the visible galaxy, perhaps 500,000 light-years or more in all directions. This dark matter halo isn't flat like the galactic disk. It's roughly spherical, meaning there's just as much dark matter above and below the galaxy as there is along the plane. In fact, if you could see dark matter, the Milky Way would look like a flat disk of stars embedded in a huge, puffy cloud of invisible material. We're literally surrounded by this mysterious substance in all directions. The large and small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere, orbit our Milky Way like cosmic satellites. The large Magellanic Cloud sits about 160,000 light-years away, positioned below the plane of our galaxy. As these galaxies orbit, they pull streams of gas above and below the Milky Way's disk. The Magellanic Stream, a ribbon of hydrogen gas stripped from these galaxies, arcs over the Milky Way's south galactic pole like a cosmic rainbow. But let's zoom out even further. As we rise above our galaxy to distances of millions of light-years, we begin to see our cosmic neighborhood in its full three-dimensional glory. The Andromeda Galaxy, our nearest large galactic neighbor, at 2.5 million light-years away, doesn't lie along the plane of the Milky Way. Instead, it's positioned at an angle slightly above our galactic plane. The local group, our small cluster of galaxies including the Milky Way, Andromeda, and about 80 smaller galaxies, is arranged in 3 dimensions. The Triangulum Galaxy, M33, sits off to one side, while dozens of dwarf galaxies are scattered above, below, and around the major galaxies like cosmic fireflies frozen in space. What's even more fascinating is that we're discovering new dwarf galaxies all the time, many of them located high above or deep below the Milky Way's plane. The Dragonfly telephoto array has revealed ultra-faint dwarf galaxies that are so dim they were hidden until recently. Some of these, like Antlia 2 discovered in 2018, orbit high above the galactic disk, invisible cosmic companions that have been there all along. The European Space Agency's Gaia mission has revolutionized our understanding of what lies above and below. By precisely measuring the positions and motions of over 1 billion stars, Gaia has revealed structures we never knew existed. Stellar streams, moving groups, and even the subtle breathing motion of our galaxy's disk as it responds to the gravitational pull of passing dwarf galaxies. One of Gaia's most stunning discoveries is the Radcliffe wave, a massive, wave-like structure of stellar nurseries that undulates above and below the galactic plane. This structure, 9,000 light-years long and 400 light-years wide, shows that even star formation in our galaxy has a three-dimensional character we're only beginning to understand. As we continue our journey upward and outward, we encounter one of the most spectacular phenomena in the universe: galactic fountains. These are massive flows of gas that get blown out of the Milky Way's disk by the combined power of thousands of supernovae. This hot gas rises thousands of light-years above and below the galactic plane before cooling and falling back down like a cosmic fountain. The Hubble Space Telescope has captured images of these galactic fountains in action. When massive stars explode as supernovae in the galactic disk, they don't just destroy themselves, they blow bubbles of million-degree gas that burst out of the galaxy entirely. This gas can travel 20,000 light-years or more above the disk before gravity pulls it back down. It's like the galaxy is breathing, exhaling hot gas and inhaling cool gas in a cycle that's been going on for billions of years. But in 2010, something extraordinary was discovered that changed our entire understanding of what lies above and below our galaxy. The Fermi Gamma-ray Space Telescope detected two enormous bubbles of gamma-ray emission extending north and south from the Milky Way's center. These Fermi bubbles, as they're now called, stretch 25,000 light-years above and below the galactic plane. That's 1/4 the diameter of the entire galaxy. These bubbles are inflated by some incredibly energetic event that happened at our galaxy's center millions of years ago. Perhaps our supermassive black hole, Sagittarius A star, had a feeding frenzy and blasted out tremendous jets of energy. Or maybe a burst of star formation at the galactic center created thousands of supernovae all at once. Whatever the cause, these bubbles are like cosmic scars, showing us that our galaxy's past was far more violent than its present. The eROSITA X-ray telescope, launched in 2019, has revealed even more structure in these regions. It discovered the eROSITA bubbles, even larger structures that encompass the Fermi bubbles and extend even further above and below the galaxy. These nested bubbles, like cosmic Russian dolls, suggest multiple episodes of explosive activity at our galaxy's heart. As we rise still higher above the galactic plane, we begin to encounter high-velocity clouds, massive clumps of hydrogen gas moving at speeds that don't match the rotation of the galaxy. Some of these clouds are falling toward the Milky Way from above and below at hundreds of kilometers per second. The Smith Cloud, discovered in 1963, is a famous example. It's currently about 8,000 light-years below the galactic plane and heading for a collision with our galaxy's disk in about 30 million years. These high-velocity clouds are like cosmic rain, bringing fresh gas from intergalactic space to fuel new generations of stars. Some may be remnants of disrupted dwarf galaxies, while others might be pristine material left over from the galaxy's formation. The Green Bank Telescope in West Virginia has mapped hundreds of these clouds, revealing a complex ecosystem of gas flowing into and out of our galaxy from all directions. But perhaps the most mind-bending discovery about what lies above and below our galaxy came from studying cosmic rays. These high-energy particles, mostly protons moving at nearly the speed of light, bombard Earth from all directions. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah have been mapping where these cosmic rays come from, and they found something remarkable. The highest energy cosmic rays don't come from within our galaxy's disk. Instead, they arrive from above and below, having traveled millions or even billions of light-years from distant galaxies. These particles carry so much energy that they can only be produced by the most extreme events in the universe: supermassive black holes devouring entire stars, or galaxies colliding at millions of miles per hour. As we venture beyond our own galaxy, rising millions of light-years above the Milky Way, we begin to see the large-scale structure of the universe itself. And here's where our concept of above and below takes on cosmic proportions. Our local group of galaxies is part of a larger structure called the local sheet, a relatively flat arrangement of galaxy groups that spans about 7 million light-years. But even this local sheet has an orientation in space. We're part of the Virgo supercluster, which contains thousands of galaxies arranged in a complex three-dimensional web. Above and below this supercluster are vast cosmic voids, regions of space containing very few galaxies. The local void, a region largely empty of galaxies, lies generally below the local sheet from our perspective. The Sloan Digital Sky Survey has mapped millions of galaxies, revealing that the universe has a foam-like structure. Galaxies cluster along filaments and walls with enormous voids between them. From any point in this cosmic web, including our own position, there are directions that lead into dense clusters and directions that lead into nearly empty voids. Our up and down happen to point toward regions of very different cosmic density. One of the most spectacular structures visible from our position is the Shapley supercluster, one of the most massive concentrations of galaxies in the nearby universe. It lies in the direction of the constellation Centaurus, which from our solar system's perspective is somewhat below the galactic plane. This gravitational monster, containing thousands of galaxies, actually pulls our entire local group toward it at about 600 kilometers per second. Meanwhile, in roughly the opposite direction, above our galactic plane from our viewpoint, lies the dipole repeller, a mysterious region of space that seems to be pushing galaxies away. Discovered in 2017, this void appears to be so empty that its lack of gravity actually influences the motion of galaxies millions of light-years away. It's as if the universe above us is pushing while the universe below us is pulling. The cosmic microwave background radiation, the afterglow of the Big Bang, shows us the ultimate backdrop to everything above and below. This ancient light comes from every direction, having traveled for 13.8 billion years to reach us. When we look at maps of this radiation from satellites like Planck and WMAP, we see tiny temperature variations that represent the seeds of all cosmic structure. Interestingly, the cosmic microwave background reveals something profound about our universe's geometry. In every direction, above, below, and all around, this ancient light tells the same story. The universe appears to be flat on the largest scales, meaning that if you could travel straight up from our position and keep going for billions of light-years, you wouldn't eventually curve back to where you started. The cosmos extends infinitely in all directions as far as we can tell. But let's bring our journey back closer to home and explore something truly extraordinary that's happening right above and below our solar system at this very moment. The Interstellar Boundary Explorer, IBEX, and the Voyager spacecraft have revealed that our solar system is moving through the local interstellar medium like a ship sailing through a cosmic ocean. And just like a boat creates a wake, our solar system creates a tail of particles streaming behind us. This heliotail extends in the opposite direction of our solar system's motion through space. Since we're moving at about 84,000 kilometers per hour relative to the local interstellar medium, this tail streams out behind us for tens of billions of kilometers. But here's the fascinating part. Because our solar system is tilted relative to our direction of motion, this tail doesn't lie in the plane of the planets. It extends at an angle, creating a three-dimensional structure that twists through space. Above our solar system's north pole and below its south pole, the interaction between the solar wind and the interstellar medium creates complex structures. The IBEX mission has detected energetic neutral atoms from these regions, revealing boundaries and shock waves we never knew existed. It's like discovering that our cosmic neighborhood has weather patterns extending far above and below the familiar plane of the planets. Let's talk about something even more mysterious: dark energy. This invisible force that's accelerating the expansion of the universe exists everywhere, above us, below us, and in every direction. The Dark Energy Survey, using the Blanco telescope in Chile, has mapped millions of galaxies to understand how dark energy affects cosmic structure. What they've found is that dark energy operates the same way whether you look up, down, or sideways from our position. It's truly universal, pushing space apart equally in all directions. The Alpha Magnetic Spectrometer aboard the International Space Station has been collecting cosmic rays from above and below Earth's poles, searching for evidence of dark matter. Some theories suggest that dark matter particles might annihilate each other in the halo above and below our galaxy, producing distinctive signatures in cosmic rays. So far, the results are tantalizing but inconclusive, another reminder that the universe above and below holds mysteries we're only beginning to explore. As we look at larger and larger scales, we encounter the cosmic web, the largest structure in the universe. The Dark Energy Spectroscopic Instrument, DESI, is currently creating the most detailed three-dimensional map of the universe ever made. It's revealing that galaxies aren't randomly scattered but are organized into a vast network of filaments and voids that extends in all directions. From our position in the universe, we can trace these cosmic filaments extending above and below the local galactic plane. The Perseus-Pisces supercluster forms a massive wall of galaxies that, from our perspective, rises above the local galactic neighborhood. Meanwhile, the southern supercluster extends below us, creating a three-dimensional tapestry of cosmic structure that's both beautiful and mind-boggling. One of the most exciting recent discoveries is the South Pole Wall, found in 2020. This massive structure of galaxies stretches across 500 million light-years and lies in the direction of what we might call below the galactic plane from Earth's perspective. It's one of the largest structures in the observable universe, yet it remained hidden until recently because it lies behind the dense star fields of our own galaxy. The concept of cosmic flows adds another dimension to our understanding of what's above and below. Galaxies aren't stationary, they're all moving through space, pulled by the gravity of massive structures. The Great Attractor, a gravitational anomaly in the direction of the Centaurus constellation, pulls thousands of galaxies, including our own, at velocities of hundreds of kilometers per second. From our solar system's orientation, this lies somewhat below the galactic plane, meaning we're being pulled downward on cosmic scales. But the flows don't stop there. Beyond the Great Attractor lies the Shapley Attractor, an even more massive concentration of galaxies. And in the opposite direction, the dipole repeller pushes galaxies away. These flows create a three-dimensional current through space, with our galaxy riding along like a leaf on a cosmic stream. We're not just orbiting the galactic center, we're part of a vast river of galaxies flowing through the universe. The Atacama Cosmology Telescope in Chile has been mapping the cosmic microwave background with unprecedented precision, revealing subtle patterns that tell us about the universe's three-dimensional structure. These patterns show that the universe looks remarkably similar in all directions, a principle called isotropy. Whether we look above or below, we see the same types of structures, the same physical laws, the same cosmic story unfolding. This isotropy is actually quite remarkable. It tells us that there's no special up or down to the universe as a whole. Every direction is equivalent on the largest scales. Yet on smaller scales, from our solar system to our galaxy to our local supercluster, there are definitely preferred directions, structures that give space a kind of geography. The 500-meter aperture spherical telescope, FAST, in China, the world's largest radio telescope, has been discovering pulsars in regions above and below the galactic plane. These spinning neutron stars act like cosmic lighthouses, and finding them in the galactic halo helps us understand the three-dimensional structure of our galaxy. Some of these pulsars have been flung out of the galactic disk by supernova explosions or gravitational encounters, now orbiting high above or far below where they were born. Let's dive deeper into one of the most enigmatic regions above and below our galaxy, the circumgalactic medium. This is a vast halo of hot, diffuse gas that extends hundreds of thousands of light-years above and below the Milky Way's disk. The XMM Newton and Chandra X-ray observatories have detected this gas at temperatures of millions of degrees, glowing faintly in X-rays. This circumgalactic medium isn't just sitting there, it's part of a continuous cycle. Gas flows up from the galactic disk blown by stellar winds and supernovae. It cools and condenses, then rains back down onto the disk like cosmic precipitation. This galactic fountain has been operating for billions of years, recycling matter between the disk and the halo. The cosmic origins. Spectrograph on Hubble has traced this cycle by studying how light from distant quasars passes through our galaxy's halo, revealing gas at multiple temperatures and velocities. What's truly extraordinary is that this recycling process has been crucial for galaxy formation. Without gas falling back down from above and below, our galaxy would have run out of raw material for new stars billions of years ago. Every star you see in the night sky, including our Sun, is made partly from material that has been through this cosmic fountain cycle multiple times. Now let's talk about something that challenges our entire conception of space: magnetic fields. The Milky Way isn't just filled with stars and gas, it's threaded with magnetic field lines that extend above and below the galactic plane. The Planck satellite, designed primarily to study the cosmic microwave background, also mapped these galactic magnetic fields by detecting polarized light from dust grains aligned with the field lines. These magnetic fields aren't confined to the galactic disk. They extend into the halo, creating complex three-dimensional structures that influence how cosmic rays propagate and how gas flows into and out of the galaxy. Some field lines loop up from the disk, arch high above the galactic plane, and dive back down like invisible cosmic rainbows. Other field lines spiral around the galaxy, creating a helical pattern that extends thousands of light-years above and below. The square-kilometre array, currently under construction in Australia and South Africa, will revolutionize our ability to map these magnetic fields. When complete, it will be able to detect faint radio emissions from cosmic rays spiraling along field lines throughout the galactic halo. This will give us the first truly three-dimensional map of the Milky Way's magnetic architecture. Above and below our galaxy, there's also a population of hypervelocity stars. Stars moving so fast they're escaping the Milky Way's gravity entirely. Some of these stars are racing upward or downward at speeds exceeding 1,000 kilometers per second. The Gaia mission has identified several dozen candidates, including some that appear to have been flung out of the galactic center by gravitational encounters with our supermassive black hole. One particularly fascinating hypervelocity star, S5HVS1, was discovered in 2019. It's traveling at 1,800 kilometers per second, fast enough to escape not just the Milky Way, but potentially even our local group of galaxies. Right now, it's rising above the galactic disk, headed for the depths of intergalactic space. In a sense, it's on the ultimate journey above our galaxy, one that will never end. The space above and below our solar system also contains something we rarely think about: interstellar dust. This isn't the same as the dust you find under your bed. It's composed of tiny grains of carbon, silicon, and iron forged in dying stars and supernovae. The Cassini spacecraft, during its mission to Saturn, detected streams of this interstellar dust flowing through our solar system from the direction of the constellation Sagittarius. Because our solar system is moving through the local interstellar medium, this dust doesn't come from all directions equally. It flows through our solar system at an angle relative to the plane of the planets, creating a kind of interstellar breeze that comes from below and to one side. The New Horizons spacecraft, now beyond Pluto, is measuring this dust and sending back data that helps us understand the three-dimensional structure of our cosmic neighborhood. Let's zoom out again and consider something truly cosmic, the dipole anisotropy of the cosmic microwave background. When we map the ancient light from the Big Bang across the sky, we find that it's slightly warmer in one direction and slightly cooler in the opposite direction. This isn't because the early universe was lopsided. It's because our entire local group of galaxies is moving through space at about 600 kilometers per second. This motion has a direction. We're moving roughly toward the Hydra Centaurus supercluster. From our solar system's perspective, this direction is somewhat below the galactic plane. So, in a cosmic sense, we're not just orbiting the galactic center, we're also falling downward through space toward a massive concentration of galaxies, hundreds of millions of light-years away. The James Webb Space Telescope has recently started observing galaxies at such immense distances that we're seeing them as they were just a few 100 million years after the Big Bang. These ancient galaxies are scattered across the sky, above us, below us, and in every direction. Each one represents a unique line of sight into the early universe, showing us that cosmic history unfolds the same way regardless of which direction we look. But here's something that might blow your mind. The observable universe has a radius of about 46 billion light-years in all directions from us. This creates a sphere centered on Earth, not because we're special, but because light has had only 13.8 billion years to reach us since the Big Bang. Any observer anywhere in the universe would see themselves at the center of their own observable universe. This means the space directly above and below our solar system contains just as much observable universe as the space in any other direction. Imagine a column extending from the south galactic pole through our solar system and out to the north galactic pole, all the way to the edge of the observable universe. This column contains superclusters, voids, billions of galaxies, and countless cosmic wonders, just as any other direction does. One of the most profound questions about what lies above and below our solar system involves the ultimate fate of the universe itself. The Dark Energy Survey has been mapping the large-scale structure of the cosmos in all directions, including regions perpendicular to the galactic plane. What they're finding is that dark energy appears to be constant and uniform throughout space, above us, below us, and everywhere else. This has enormous implications. If dark energy continues to accelerate the expansion of the universe, structures above and below us will eventually be carried beyond our cosmic horizon. In about 150 billion years, galaxies beyond our local group will have receded so far that their light can never reach us. The universe above and below will simply vanish from view, leaving future astronomers in a much lonelier cosmos. But in the nearer term, astronomically speaking, something dramatic is going to happen above our solar system's northern sky. The Andromeda Galaxy is approaching us at about 300 kilometers per second. In roughly 4 billion years, Andromeda will collide with the Milky Way. Computer simulations show that this merger will fling stars and gas thousands of light-years above and below the plane of both galaxies. The Hubble Space Telescope has actually measured Andromeda's sideways motion with incredible precision, using stars as reference points. These measurements confirm that the collision is inevitable. When it happens, our Sun might be thrown high above or deep below the merged galaxy's new disk. Future inhabitants of Earth, if any exist, will see the night sky transformed, with stellar nurseries blazing above and below like cosmic fireworks. Speaking of transformations, let's discuss something happening right now above and below our galaxy, the formation of new satellite galaxies. The Dark Energy Camera has discovered dozens of ultra-faint dwarf galaxies orbiting the Milky Way. Many of these tiny galaxies orbit in nearly polar orbits, meaning they swing far above the galactic North Pole and far below the South Pole on each orbit. These dwarf galaxies are like cosmic fossils containing some of the oldest stars in the universe. By studying their orbits and composition, astronomers can reconstruct the Milky Way's assembly history. Each dwarf galaxy that orbits above and below the galactic plane is a piece of a cosmic jigsaw puzzle, telling us how our galaxy grew through mergers and accretion over billions of years. The search for gravitational waves has also revealed something fascinating about the space above and below. The LIGO and Virgo detectors have caught gravitational waves from merging black holes and neutron stars. Some of these cosmic collisions occurred in galaxies that lie well above or below the galactic plane from our perspective. The waves travel through space equally well in all directions, carrying information across the universe at the speed of light. The upcoming LISA mission, the Laser Interferometer Space Antenna, will be positioned in space itself, forming a triangle of spacecraft that can detect lower-frequency gravitational waves. LISA will be sensitive to waves from supermassive black hole mergers occurring anywhere in the universe, including in galaxies directly above or below the galactic plane. This will give us a new way to explore the three-dimensional structure of the cosmos. Let's talk about something that exists literally everywhere, above and below us: quantum fields. According to quantum field theory, every point in space is filled with fields corresponding to different particles: the electron field, the quark field, the Higgs field, and so on. These fields extend infinitely in all directions. When these fields vibrate in just the right way, they create the particles we observe. This means that the space above your head right now and the space below your feet is seething with quantum activity at scales too small to observe directly. The Large Hadron Collider in Switzerland can excite these fields and create new particles, but the fields themselves exist everywhere, including in the emptiest voids between galaxy clusters. The vacuum of space isn't truly empty. Recent measurements from the Planck satellite have allowed physicists to calculate the vacuum energy density, the energy inherent in empty space itself. This energy is the same whether you're in the galactic disk or 100,000 light-years above it. It's a universal constant that fills all of space, contributing to the mysterious dark energy that's accelerating cosmic expansion. Here's something that connects the very small to the very large: cosmic rays. These high-energy particles rain down on Earth from all directions, including from directly above and below the solar system's plane. The IceCube Neutrino Observatory, buried deep in the Antarctic ice, can detect neutrinos coming through the entire Earth from the northern sky. These neutrinos and cosmic rays originate from some of the most violent events in the universe. Some cosmic rays come from supernovae in our galactic neighborhood. Others arrive from active galactic nuclei billions of light-years away. The most energetic cosmic rays, those with energies exceeding 10 to the 20th electron volts, might come from sources we haven't even identified yet. The Pierre Auger Observatory in Argentina has been mapping these ultra-high-energy particles, trying to trace them back to their sources among the galaxies above and below the galactic plane. The solar system's motion through the galaxy creates another fascinating effect in the space above and below us. As we orbit the galactic center, we periodically pass through the spiral arms of the Milky Way. These passages, which happen roughly every 100 million years, might expose us to increased cosmic ray flux and nearby supernovae. Some scientists have even proposed that mass extinctions on Earth might correlate with our passages through spiral arms. Right now, we're in the Orion Spur, a minor spiral arm. In about 10 million years, we'll begin entering the Perseus Arm, which lies somewhat above our current position in the galaxy. This journey through the galactic disk's vertical structure could potentially affect Earth's climate and the evolution of life through increased radiation exposure. The breakthrough. Listen Project, searching for signals from extraterrestrial civilizations, scans the sky in all directions, including above and below the galactic plane. If intelligent life exists elsewhere in our galaxy, there's no reason it should be confined to the galactic disk. Globular clusters, which orbit high above and below the plane, might harbor ancient civilizations billions of years older than humanity. We're listening for their signals in the cosmic silence. Let's explore one of the most mind-bending concepts about the space above and below us, cosmic inflation. In the first tiny fraction of a second after the Big Bang, specifically from about 10 to the negative 36 seconds to 10 to the negative 32 seconds, the universe underwent a period of exponential expansion. During this incredibly brief moment, space itself expanded faster than the speed of light, growing from subatomic scales to something larger than our entire observable universe today. This inflation happened in all directions equally, up, down, and sideways, from any point you could choose. The consequences are still visible today in the cosmic microwave background radiation. The Planck satellite has measured the temperature fluctuations in this ancient light with exquisite precision, finding that they match the predictions of inflation theory remarkably well. What this means for the space above and below us is profound. The observable universe we see in any direction is just a tiny fraction of the total universe created by inflation. Beyond our cosmic horizon in every direction, including straight up and straight down, the universe continues far beyond what we can ever observe. There might be countless other galaxies, superclusters, and cosmic structures in these unreachable regions, forever hidden from our view. The concept of the multiverse takes this even further. Some versions of inflation theory suggest that our universe is just one bubble in an eternally inflating cosmos. Other bubble universes might exist beyond ours in a higher dimensional space, each with potentially different physical laws. While this remains highly speculative, it represents the ultimate expansion of what might lie beyond, not just above and below our solar system, but beyond the very fabric of our space-time itself. Let's return to something more concrete, but equally fascinating: the cosmic microwave background's polarization patterns. The Atacama Cosmology Telescope and the South Pole Telescope have been mapping these patterns in unprecedented detail. The polarization encodes information about the three-dimensional structure of the universe when it was just 380,000 years old. These measurements reveal that density fluctuations existed in all directions in the early universe. Some regions were slightly denser, others slightly less dense. Gravity amplified these fluctuations over billions of years, creating the cosmic web we see today. The structures above and below the galactic plane, the voids, filaments, and clusters, all trace back to quantum fluctuations in the first fraction of a second after the Big Bang. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct the largest survey of galaxies ever attempted. It will map hundreds of millions of galaxies in 3 dimensions, revealing the cosmic web structure in unprecedented detail. This will include vast regions above and below the ecliptic plane and galactic plane that have been less thoroughly surveyed until now. One of Roman's key missions is to study dark energy by measuring how cosmic structure has evolved over billions of years. By comparing the distribution of galaxies in different directions and at different distances, including regions directly above and below us in cosmic space, astronomers hope to understand whether dark energy's strength has changed over time. The Vera Rubin Observatory in Chile, which began operations recently, is conducting the Legacy Survey of Space and Time. Over 10 years, it will photograph the entire visible sky every few nights, creating an unprecedented movie of the changing cosmos. This will reveal transient events like supernovae, asteroid passages, and variable stars throughout the three-dimensional volume of space surrounding us. As we contemplate the vastness above and below, it's worth reflecting on how our understanding has evolved. Ancient civilizations saw the sky as a dome overhead, with an underworld below. Medieval astronomers placed Earth at the center of nested celestial spheres. Copernicus and Galileo moved Earth from the center, but still imagined space as having an edge. Today we know there's no edge, no center, no absolute up or down. We're part of a universe that extends far beyond what we can see, with structures and phenomena that exist in all directions. The space above our solar system's north pole contains the same laws of physics, the same types of galaxies, and the same cosmic evolution as the space below our south pole. Yet from our particular vantage point, these directions do have meaning. They define our orientation in the Milky Way, our relationship to nearby structures, and our motion through cosmic space. We're not at the universe's center, but we are at the center of our own cosmic perspective, the only perspective we can ever have. The Cosmic Evolution Early Release. Science survey conducted with the James Webb Space Telescope has been observing galaxies at the edge of the observable universe in multiple directions across the sky. What they're finding is that galaxy formation appears to have followed similar patterns in all directions. Whether JWST points toward the galactic North Pole or South Pole, toward rich clusters or empty voids, the early universe looks remarkably consistent. This cosmological principle, that the universe looks the same in all directions on large scales, is one of the foundations of modern cosmology. It tells us that the laws of physics and the cosmic story are universal. A civilization in a galaxy 10 billion light-years away, in the direction we call above the galactic plane, would see a universe that follows the same rules and exhibits the same large-scale structure as we do. As we bring our cosmic journey to a close, consider this. Every direction you can point from Earth leads to infinity. Above your head, below your feet, and in every direction in between, the universe extends beyond our ability to observe or comprehend. The space above and below our solar system isn't empty or simple. It's filled with layers of structure, from the solar wind to stellar streams, from galactic fountains to cosmic filaments, from dark matter halos to the very fabric of space-time itself. Our sun, planets, and every atom in your body are positioned in three-dimensional space with a particular orientation. We're tilted 60 degrees to the galactic plane, bobbing up and down through it over hundreds of millions of years. We're embedded in the Milky Way's disk, surrounded by a spherical halo of dark matter and ancient stars. We're part of the local group, situated in the local sheet, flowing through the cosmic web toward the Shapley attractor. From this unique position, we can look up and down, north and south, in and out. And in every direction we look, we find wonders, pulsars spinning in the galactic halo, dwarf galaxies orbiting in polar loops, hot gas fountaining above and below the disk, cosmic rays from distant galaxies, gravitational waves from merging black holes, and the ancient light of the Big Bang coming from every point on the celestial sphere. The space above and below our solar system is not separate from us. It's part of the same cosmic ecosystem that created us. The atoms in your body were forged in stars that might have been high above or far below the galactic plane. The supernova that scattered those atoms could have exploded anywhere in the galaxy. The dark matter that dominates the mass above and below helped shape the gravitational potential that allowed our galaxy to form and our solar system to coalesce. We are not observers looking up at the universe from below or down at it from above. We are the universe looking at itself, matter and energy organized in just the right way to ask questions and seek answers. The mystery of what lies above and below our solar system is really the mystery of what we are made of, where we came from, and how we fit into the cosmic story that's been unfolding for nearly 14 billion years. Every time you look up at the night sky, or imagine looking down through the Earth to the cosmos below, you're peering into the same endless universe. Above and below are just directions we assign from our temporary vantage point. In reality, we're surrounded on all sides by infinity, embedded in a cosmos that's far grander, stranger, and more beautiful than our ancestors could have imagined, and we've only just begun to explore it. Let's delve deeper into something we touched on but deserves much more attention: the role of time in understanding what's above and below our solar system. When we look up or down into space, we're not just looking across distance, we're looking backward through time. Light has a finite speed, so the photons entering our telescopes left their sources years, centuries, or even billions of years ago. The globular cluster, Messier 15, sitting about 33,000 light-years above the galactic plane, appears to us as it was 33,000 years ago when modern humans were just beginning to spread across Earth. The stars we see in that cluster might have changed dramatically since then. Some might have exploded as supernovae, others might have evolved into white dwarfs. We won't know until their light from those events reaches us, thousands of years in our future. This temporal dimension becomes even more dramatic when we look at distant galaxies above and below the local galactic neighborhood. The galaxy cluster, Abell 2185, located roughly perpendicular to the galactic plane at about 3 billion light-years away, appears to us as it existed 3 billion years ago, before our Sun even formed. We're seeing ancient light from a time when the universe was 70% of its current age. The Hubble Ultra Deep Field and the subsequent James Webb Deep Field images have revealed galaxies in all directions across the sky, including regions above and below the ecliptic and galactic planes. Some of these galaxies appear as they were just a few 100 million years after the Big Bang. When we look at them, we're literally seeing into the cosmic dawn, the era when the first stars ignited and began to illuminate the universe. What's remarkable is that we can compare galaxies at different distances in the same direction, say straight above the galactic North Pole. We can see galaxies at 1 billion light-years, 5 billion light-years, and 10 billion light-years, creating a timeline of cosmic evolution in that particular direction, through space. Each shell of distance is a snapshot of the universe at a different age. The South Pole Telescope has been conducting deep surveys of a region of sky that, from Earth's perspective, is literally straight down, through the planet and out the other side toward the South Celestial Pole. This region happens to include some of the most distant galaxy clusters ever discovered, allowing astronomers to study how these massive structures formed and evolved in this particular cosmic direction. Now let's explore something truly exotic: the potential for different phases of space itself above and below us. Quantum field theory suggests that the vacuum of space can exist in different energy states. Some theories propose that our universe might be in a false vacuum, a locally stable but not absolutely stable state. If true, a bubble of true vacuum could nucleate anywhere in space and expand at the speed of light, fundamentally changing the laws of physics. If this happened somewhere above or below our galaxy, say 100 million light-years away, we would have no warning. The bubble would expand toward us at light speed, and we would see it only at the moment it reached us. The space above and below us could already contain such bubbles, expanding toward us from distances so great that they won't arrive for billions of years. Or we might be completely safe with our vacuum being the true ground state after all. The Planck satellite's measurements of the cosmic microwave background have placed tight constraints on these vacuum instability theories. The universe appears to be remarkably stable on cosmic scales. Whatever exists above and below us seems to follow the same physical laws we observe locally, at least over the 13.8 billion years that light has been traveling to reach us. Let's discuss the theoretical possibility of extra dimensions. String theory and other quantum gravity frameworks suggest that space might have more than 3 dimensions. These extra dimensions could be compactified, curled up so small we can't detect them, or they could extend infinitely in directions we can't perceive. If extra dimensions exist, they would be present everywhere, including above and below our solar system. The Large Hadron Collider has searched for evidence of extra dimensions by looking for particles or energies that seem to disappear, potentially leaking into other dimensions. While nothing conclusive has been found, the possibility remains that the space all around us, above, below, and in every direction, has hidden dimensional structure we're only beginning to imagine. The concept of the holographic principle suggests something even stranger, that all the information contained in a 3-dimensional volume of space can be encoded on its 2-dimensional boundary. This idea emerged from black hole physics but might apply to the universe as a whole. If true, the vast spaces above and below our solar system might be holographic projections from a cosmic boundary we can't directly observe. Recent work on the ADS-CFT correspondence, a mathematical relationship between gravity in higher dimensions and quantum field theory in lower dimensions, suggests these ideas might be more than philosophical speculation. They could represent deep truths about the nature of space-time itself. The space above your head right now might be fundamentally holographic, with all its information somehow encoded on a distant cosmic screen. Let's return to observable phenomena and discuss the Sunyaev-Zeldovich effect, which lets us detect galaxy clusters through their influence on the cosmic microwave background. The Atacama Cosmology Telescope has used this effect to discover hundreds of massive galaxy clusters, some located in regions above and below the galactic plane that are difficult to survey optically due to foreground stars and dust. This technique reveals the 3-dimensional distribution of matter throughout the observable universe. By mapping galaxy clusters at different distances in different directions, including straight above and below the galactic plane, astronomers are creating the most comprehensive picture yet of cosmic, large-scale structure. The space above and below us contains the same rich tapestry of clusters, filaments, and voids as any other direction. One of the most exciting frontiers in understanding what lies above and below our solar system involves neutrino astronomy. Neutrinos are ghostly particles that barely interact with matter, allowing them to pass through entire planets as if they weren't there. The IceCube Neutrino Observatory at the South Pole has detected neutrinos coming from all directions, including straight up through the Earth from the northern sky. In 2017, IceCube detected a high-energy neutrino that had traveled through the entire Earth from a direction above the northern hemisphere. By tracing this neutrino back to its source, astronomers identified a blazar, a galaxy with a supermassive black hole shooting a jet directly toward Earth, located 4 billion light-years away. This single neutrino had traveled straight down through cosmic space for 4 billion years before passing through our entire planet and being detected in Antarctic ice. This discovery opened a new way to explore the universe in all directions. Unlike light, neutrinos can escape from the densest regions of cosmic catastrophes. They travel in straight lines, undeflected by magnetic fields. The KM3-NET neutrino telescope, currently being built in the Mediterranean Sea, and the proposed IceCube Gen 2 expansion will soon detect neutrinos from every direction, creating a three-dimensional map of the universe's most violent events. Now let's talk about something that exists everywhere above and below us but remains completely mysterious: the inflaton field. This hypothetical field supposedly drove cosmic inflation in the first fraction of a second after the Big Bang. If it exists, it fills all of space, including the regions above and below our solar system. The field's energy has mostly dissipated, but quantum fluctuations in the inflaton might have seeded all the cosmic structure we see today. The BICEP and Keck array telescopes at the South Pole search for evidence of the inflaton by looking for a specific pattern in the polarization of the cosmic microwave background, a swirling pattern called B-mode polarization that would be the signature of gravitational waves from inflation. They scan regions of sky near the South Celestial Pole, looking above and beyond our galaxy for evidence of the universe's first moment. These experiments face a significant challenge. Our own galaxy produces polarized light from magnetic fields threading through interstellar dust. This foreground emission is strongest along the galactic plane, but extends above and below it. Astronomers must carefully model and subtract this galactic contamination to reveal the faint, primordial signal from the Big Bang itself. Let's explore the concept of cosmic voids in more detail. These are vast regions of space containing very few galaxies, and they exist above and below the galactic plane just as they do in other directions. The Bootes void, discovered in 1981, spans 330 million light-years and contains only 60 known galaxies, compared to the 10,000 you'd expect in such a volume. What's fascinating is that voids aren't completely empty. They contain dark matter, diffuse gas, and occasional orphan galaxies. The Dark Energy Spectroscopic Instrument is currently mapping these voids in 3 dimensions, including their vertical extent relative to the galactic plane. Understanding void structure helps us comprehend how dark energy and cosmic expansion have shaped the universe. Voids actually expand faster than the average cosmic expansion rate. As structure forms, matter flows out of voids and into filaments and clusters, making the voids progressively emptier. If there's a large void above or below our position in space, its expansion affects the motion of galaxies around it. The dipole repeller we mentioned earlier might be such a void, pushing galaxies away through its very emptiness. Now let's discuss something happening right now in the space above and below our solar system: stellar streams being tidally stripped from dwarf galaxies. The Gaia spacecraft has discovered dozens of these streams, rivers of stars stretched across the sky by the Milky Way's gravity. Many of these streams have significant vertical components, arcing high above or plunging far below the galactic disk. The GD1 stream, for example, is a thin river of stars from a disrupted globular cluster that extends more than 60 degrees across the sky. Its orbit carries it thousands of light-years above and below the galactic plane. By studying such streams, astronomers can map the 3-dimensional distribution of dark matter in our galaxy's halo, the invisible mass that exists all around us, above and below. Some stellar streams show gaps and clumps that might be caused by encounters with dark matter subhalos, smaller concentrations of dark matter orbiting within the Milky Way's larger halo. These interactions would happen in the 3-dimensional space surrounding our galaxy, including regions far above and below the disk. Each perturbation in a stellar stream is like a cosmic breadcrumb trail leading to invisible dark matter structures. The concept of the local bubble provides another perspective on what's above and below us on a smaller scale. We're currently inside a region of hot, low-density gas about 1,000 light-years across, created by supernova explosions over the past 10 to 20 million years. This bubble extends above and below the galactic plane, and we're currently located slightly below its center. The eROSITA X-ray telescope has mapped this hot gas in 3 dimensions, revealing that it's not spherical but elongated and connected to other bubbles created by stellar feedback. The Sun is currently moving upward through this structure, having entered from below. In about 5 million years, we'll exit the top of the local bubble and enter a different region of the interstellar medium. Let's talk about rogue planets, worlds ejected from their stellar systems and wandering through space alone. Computer simulations suggest there might be billions of these orphan worlds in our galaxy, including in the regions above and below the galactic plane. The Nancy Grace Roman Space Telescope will search for these dark wanderers through gravitational microlensing, potentially revealing a hidden population of planets drifting through the galactic halo. Some of these rogue planets might have been flung upward or downward out of the galactic disk entirely, sailing through the halo on parabolic trajectories that will eventually take them into intergalactic space. Others might orbit the galaxy in highly inclined paths, spending most of their time far above or below the stellar disk. These lonely worlds represent a completely different planetary environment: no sun, eternal darkness, temperatures approaching absolute zero. The search for primordial black holes adds another dimension to what might exist above and below us. These hypothetical objects would have formed in the first second after the Big Bang from density fluctuations, not from stellar collapse. If they exist, they could be anywhere, including in the galactic halo above and below the disk. Some theories suggest primordial black holes might constitute some or all of dark matter. The Subaru Hyper-Suprime Cam has searched for these objects by looking for gravitational microlensing events caused by compact objects passing in front of distant stars. By surveying regions above and below the galactic plane and monitoring millions of stars, astronomers hope to detect the telltale brightening that would reveal a primordial black hole. So far, the constraints suggest that if they exist, they can't make up all of dark matter, but they might be part of the mix. As we approach the culmination of our cosmic journey, let's explore one of the most profound questions about the space above and below our solar system. What will be there in the distant future? The universe is not static, it's evolving, and the regions above and below us will look dramatically different billions of years from now. In about 4 billion years, when the Milky Way and Andromeda galaxies collide, the entire concept of above and below our galaxy will transform. Computer simulations of this merger show that stars will be flung in all directions. The supermassive black holes at the centers of both galaxies will spiral toward each other, eventually merging in a cataclysmic event that will reshape the combined galaxy's structure. During this merger, our Sun might be thrown thousands or even tens of thousands of light-years above the new galaxy's plane. From Earth, if it still exists, the night sky would be ablaze with stellar nurseries as gas clouds collide and trigger furious star formation. Looking up and down from our new position, we'd see a completely reorganized cosmic neighborhood, with globular clusters redistributed and stellar streams tangled into new configurations. But the changes extend far beyond our local galactic merger. The expansion of the universe, driven by dark energy, will carry distant galaxy clusters beyond our cosmic horizon. The Virgo cluster, currently 54 million light-years away, in a direction roughly perpendicular to the galactic plane, will eventually recede beyond the point where its light can ever reach us. The space in that direction will appear progressively emptier as structure after structure vanishes from view. In about 100 trillion years, if current dark energy models are correct, every galaxy beyond our local group will have disappeared beyond the cosmic horizon. Future astronomers in that distant era, looking up and down from wherever their civilization might be located, will see a universe containing only their local merged galaxy surrounded by absolute cosmic darkness. The rich, three-dimensional tapestry of structure we observe today will have been erased by expansion, but even this isn't the end. Current theories suggest that in 10 to the 100 years, even the merged remnant of our local group will have evaporated. Every star will have died, every black hole will have evaporated through Hawking radiation, and the universe will enter what physicists call the dark era, a cold, empty void extending infinitely in all directions, including above and below any remaining structure. Yet this far future also holds possibilities we're only beginning to imagine. Some theories suggest that random quantum fluctuations over unimaginable timescales could spontaneously create new structures, perhaps even new universes. The space above and below our position in this distant future might witness the birth of bubble universes, each with potentially different physical laws. Let's return to the present and discuss what cutting-edge missions will reveal about the space above and below us in the coming decades. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter, large enough to collect 13 times more light than any current optical telescope. This instrument will be able to directly image exoplanets in our stellar neighborhood, including those in star systems above and below the galactic plane. It will study the atmospheres of these worlds, searching for biosignatures, gases that might indicate the presence of life. Imagine discovering that the first evidence of extraterrestrial life comes from a planet orbiting a star high above the galactic plane in a direction we rarely think about when we contemplate our cosmic neighbors. The square-kilometer array, when completed, will be 50 times more sensitive than any current radio telescope. It will map neutral hydrogen throughout the Milky Way and beyond, revealing the three-dimensional structure of gas in the galactic halo. This will show us exactly how material cycles between the disk and regions above and below, completing our picture of the galaxy as a living, breathing ecosystem. NASA's proposed Habitable Worlds Observatory will search for signs of life on planets around nearby stars. Some of these target stars will inevitably lie above or below the ecliptic plane, the flat disk of our solar system. Finding life on a planet around a star tilted far out of our planetary plane would emphasize that life's potential extends in all three dimensions of space, not just along the plane where Earth happens to orbit. The Cosmic Microwave Background Stage 4 experiment, or CMBS-4, will deploy thousands of detectors at the South Pole and in the Atacama Desert, mapping the earliest light in the universe with unprecedented precision. By observing the sky in all directions, including straight up and down from our position in the galaxy, these instruments will probe the first moments after the Big Bang, testing our theories of cosmic inflation and the birth of structure. Let me share something that brings our journey full circle. We are intimately connected to everything above and below us. The calcium in your bones was created in a supernova that might have exploded far above the galactic plane billions of years ago. The iron in your blood could have come from a Type Ia supernova in the galactic halo. The oxygen you're breathing right now was forged in massive stars that could have been anywhere in the three-dimensional volume of our galaxy's history. Every atom in your body has traveled through space for billions of years, cycling through the galactic fountain, being flung upward in supernova explosions, condensing in molecular clouds that might have been high above the disk, and eventually finding its way to the solar nebula that formed our sun and planets. You are made of material that has explored the full three-dimensional extent of our galaxy long before you existed to ask about it. The gravitational waves washing over Earth right now have traveled through the space above and below us from colliding black holes throughout the universe. The neutrinos passing through your body every second come from the Sun, from supernovae in all directions, and from the Big Bang itself. The cosmic microwave background photons that fill the space around you have been traveling for 13.8 billion years from every direction simultaneously. We are not separate observers looking up at a distant universe or down through Earth to an abstract cosmos. We are integral parts of a universe that extends infinitely in all directions. The space above your head contains the same fundamental forces, the same dark matter, the same dark energy, and the same quantum fields as the space below your feet. You exist at the intersection of countless cosmic processes that have operated throughout all of space for nearly 14 billion years. When ancient humans looked up at the night sky, they saw a dome of lights above them and imagined an underworld below. When medieval astronomers studied the heavens, they placed Earth at the center of nested crystal spheres. When early modern scientists embraced heliocentrism, they still imagined space as having a center and an edge. Today, we know better. There is no up or down to the universe. There is no center or edge. Every point in space is equivalent to every other on the largest scales. The space above our solar system's north pole contains the same types of structures, following the same laws of physics, participating in the same cosmic evolution as the space below our south pole. Yet from our particular vantage point, a small planet orbiting an ordinary star in the suburbs of a typical galaxy, these directions do have local meaning. They define our orientation in the Milky Way. They show us where to look to see ancient globular clusters versus young star-forming regions. They determine which nearby stars we encounter as our solar system bobs up and down through the galactic plane. They structure our view of the cosmic web, determining which superclusters and voids lie in which directions. As our instruments become more powerful and our understanding deepens, we continue to discover wonders in every direction. Above and below the galactic plane, we find stellar streams and hypervelocity stars, superbubbles and galactic fountains, dark matter and missing satellites. Above and below the local cosmic web, we see vast voids and massive superclusters, ancient light and future horizons. The journey from asking what's above and below our solar system has taken us from the sun's polar jets to the edge of the observable universe, from quantum fields to cosmic voids, from the present moment to the far future and distant past. What we've discovered is that the universe is far richer, stranger, and more beautiful than the simple mental models of up and down, above and below. Every direction from Earth leads to infinity, or at least to the horizon of observability set by the finite age of the universe and the speed of light. The cosmos doesn't care about our human concepts of verticality. It extends in all directions with equal majesty, equal mystery, and equal invitation to explore and understand. So the next time you look up at the night sky, remember that you're not looking up into something separate from yourself. You're looking out into the same universe that extends in every direction, including down through the earth beneath your feet. You're seeing light that has traveled through three-dimensional space from stars and galaxies distributed throughout the cosmic web. You're witnessing a universe that's simultaneously incomprehensibly vast and intimately connected to every atom of your being. The space above and below our solar system isn't just empty void or distant abstraction. It's filled with stars and galaxies, dark matter and energy, quantum fields and gravitational waves, neutrinos and cosmic rays. It's the same universe that created us, the same cosmos we're made of, the same reality we're part of. And perhaps most wonderfully, it's a universe we're only beginning to understand, with mysteries above, below, and in every direction waiting to be discovered by curious minds looking up at the stars and asking, what's out there? If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. Will we ever leave our solar system? In this video, we explore the science, technology, and human challenges behind interstellar travel and humanity's quest to reach the stars. See you there.